Hi, everybody. Um, this is our third lecture this week, believe it or not. This week's felt long, and I'm sure it feels long for you guys. This lecture covered chapter 9, which is all about momentum, which is yet another way to look at Newton's laws and how they predict motion, which again, I cannot emphasize strongly enough that is the whole point of this course, is to be able to observe motion and predict what future motion will be and understand how that motion changed. At the end of this video is going to be a little bit longer than normal, but at the end of this video, I'll have a final slide that will tell you basically the 6 things that you really need to know. One kind of nice thing is the equations are pretty simple, pretty straightforward once we derive them. And it's more plug and chug, meaning more just figure out what equation you want, put some numbers in and get an answer than previously. So this stuff, you need to draw for yourself what's going on and kind of label things like we've always done. But it's a lot easier as far as figuring out what you're being asked to use, what tools are important. So that being said, we're going to start off, we'll talk about what momentum is, where it comes from, the ideas behind it, and then we're going to talk about center of mass. And center of mass is not the funnest topic in the world. In fact, it's not super useful to us. The idea is, but the way you determine it isn't, and we'll talk about why. And then we'll move on to doing cool stuff with momentum, a lot of fun problems. Momentum's fun because it's real world stuff. Of everything we've done so far, momentum has the largest impact on any real world situation that you want to try to figure out. You can go home and use this to figure out all sorts of stuff. It's actually really important, really useful. Might be the true or the closest framework we have so far for getting answers to what's actually happening in the world as far as motion is concerned. So let's talk about momentum. We're going to, again, take another look at Newton's laws. And we're going to look at really what he was saying. You learned F equals ma, but really how Newton described it was something different entirely. So if we take our equation, F equals ma, and we remember that a is the time derivative of the velocity, right? So we can plug in for a dv dt. We did this last time when we were talking about energy, but we're going to do this a little bit differently now. So if we look at this, assuming that mass is constant, but we can always move it into our derivative. And when we do that, what we get is we get this product, mass times velocity. That product is something called momentum. And really what a force does is it's the time rate of change of the momentum. A force changes the momentum of a system. This says mv. A system could be one mass, it could be an infinite collection of masses. But when we apply an external force, we get a change in the momentum of our system. And that's really important. The reason why it's important is just like with energy, if this force were 0, we would have no change in the momentum. That doesn't mean that the momentum can't change. It means that the value of the initial momentum and the final momentum will be the same. And that's a very important conservation rule. That might be the most important conservation rule, is that in the absence of forces, the momentum of a particle doesn't change. A few things that we need to talk about before we go any further, and that's that if a particle or a system was moving relative to a three-dimensional coordinate axis, it can have momentum in the x and in the y and in the z, but they're independent of each other. You could find out what the magnitude of the final momentum is, and that we would do the normal way, px squared plus py squared, etc. And we could figure out what angle this makes to, say, the x-axis using trigonometry. But in general, in this course, we're just going to talk about one and two-dimensional momentum, and you treat them separately. You treat the momentum in each unit direction or each direction as its own momentum. That's super important. And then you can sum them to find the final momentum, obviously. The other thing is momentum, because it's based on velocity, is in fact a scalar. Mass is is in fact a vector. Mass is a scalar, but velocity is a vector. Therefore, the momentum is obviously a vector. One weird note, I've always found this weird, is if we look at the units of momentum, which, as I said, momentum might be one of the cardinal quantities, the most important quantities that any system or object has. This is kilograms for mass, meters per second. And there's no name for momentum. It's not a joule, it's not a Newton, it's not a watt, it's not a Pascal. Momentum is just momentum, which is a little weird. You would think that if it's so important, we should have a unit identifying what it is. Rather hilariously, if you go to somewhere like Reddit, people will talk about moms, that the units of momentum are moms. They're not. There's no official designation of a unit for momentum. It's just momentum. Another way to look at this is that this would be a Newton times time. Because if we multiply, a Newton has a second in the bottom, so if we do this, we get kilograms meters per second squared times time. So momentum is force times time. We can actually see that here if we move the dt to the opposite side of the equation, multiply through by dt. And that's going to be something called impulse that we'll talk about soon. But momentum, it's a vector. The units have no name, and it can be found in either the x, y, or z direction, independent of the other directions. You can change the momentum in the y, you can change the momentum in the x, you can change the momentum in the z. It won't affect the momentum of the other directions. That's really important in general. And so you might, if you think about this, realize how simple and elegant this really is. Because we don't have to take a time derivative. We don't have to take a derivative. We're not worried about the acceleration. All we care about is the velocity and the mass of the particle or system. And velocity is something that we as humans can measure really accurately without even graphs or anything else. You can pull out a stopwatch or count time in your head or whatever you want and figure out how far something traveled in a certain amount of time and figure out how that changes based on when you apply forces. It's really, really elegant because it's simple and it actually gives really good predictions. Yeah, so sorry, someone's making coffee. Is that you making coffee, Les? Oh. It's all right. I just didn't want them to think there was like a hose going out or something. Anyway, sorry, that was my wife. So yeah, that is basically momentum. If you go back and you restate Newton's laws, right, the momentum of a particle stays the same unless acted upon by force. So if you kind of change an object at rest with zero momentum, stays at rest. An object in motion stays in motion. The momentum stayed constant unless acted upon by a force. And force is the rate of change of the momentum of an object. From this, we see here, as I said, if we move dt to the opposite side of the equation and integrate, what we get is we get the force times time is equal to the change in momentum. Now, the conservation law comes in, where if there's no net force, then the initial and final momentum, which is what these are, the final momentum is equal to the initial momentum. And you might say, well, yeah, that doesn't look that interesting, except it really actually is, because we're talking about not just single particles, but systems of particles. And that means that if the initial momentum, let's say the system contained two masses connected by a spring or something, right? And if the initial momentum was m1 initial and times v1 initial, m2 v2 initial has to equal m1 v1 final plus m2 v2 final. And that means that even though there's no net force on a system, they could exchange their velocities and it wouldn't violate the conservation of momentum. It's actually pretty cool. It's pretty useful. That in itself we'll actually get to more when we talk about angular momentum. But yeah, a system can change its momentum of the individual parts as long as the net momentum doesn't change and it's not a violation of the conservation law. That becomes super important. So the conservation of momentum comes in when there's no net force. Force adds or takes away momentum. So if there's no net force, the initial and final momentums are the same. That's conservation. When the force is present, what happens is you get something called an impulse, and we'll talk about that after we talk about center of mass. But an impulse changes the momentum. And because momentum is a vector and forces are vectors, you could lose momentum or gain momentum in a particular direction based on the force. We'll get there, you'll see, it's not too bad. But we need to talk about something a little bit more important. This is one of the things that I think Newton actually doesn't get enough credit for. It's one of his observations that people don't talk too much about. And he realized that when he was trying to figure out why an object fell toward the ground, he realized that if you try to figure out where the center of gravity is, that basically for any solid, no matter what shape it is, you can select a point where it acts as if all the mass were a point particle. That means that every system, every object, can act as if its center of mass is at some central point. And then when you do your analysis of the motion, you just assume that it's a point particle with that mass. So the Earth has a mass of 5.97 kilogram times 10 to the 24 kilograms. It acts like all of that mass is an unmeasurable point, an infinitely small point at the center of the Earth. But where is that center of Earth? Where is the center of mass of a system? It's really easy on a point particle, but on a system, it gets harder. And why we need it is we see that the net momentum is all the MVs for each particle. What this IV means is I could have a system with 3 different masses, and each of these masses has its own velocity vector, right? So this is V1, and this is V2, and this is V3 initially. And so what I'd have to do to get the net momentum is multiply the mass of 1 times V1, plus the mass of 2 times V2, plus the mass of 3 times V3. And then at some later time, maybe, mass 1 is headed in this direction, and this is now final, and mass 2 is off headed in this direction, and mass 3 is headed off in this direction, right? I can add those momentum up and get the final. However, it's easier to figure out where the center of mass is and find the net. So this is the mass of the center of mass, and find the net and compute that momentum. So the momentum is really the net momentum times the velocity, or sorry, the net mass times the velocity, the sum of the masses times their velocities. But we're going to have to figure out what that center of mass is and how to find it if we don't have a point particle. And it turns out there's a lot of easy ways to do this. There's some some tedious algebra that we need to do. That's not very hard, but it's super tedious. But there's going to be something called symmetry. So as I said, one of Newton's greatest contributions was that he realized for a uniform body, a body with uniform density, right? You can figure, and it doesn't even have to be uniform density, but for us, the uniform density, if it has a uniform density, we can find its center of mass, and then it acts as if it's a particle with all of its mass at the center. And when I say act, what that means is we only have to figure out the net acceleration at that point to figure out what anything in that system is doing. That's really, really important. Think of it this way. The Earth is rotating around the sun, and we don't worry about each little tiny mass. We don't worry about the mass of each person. We know the Earth as a whole planet is moving. And it's moving as if all of the mass of the Earth is at the center of the Earth around the sun. So one of the problems with humans is we're actually not that smart. Some of us are very smart, but in general, we need things as simple as possible is what I mean. Simple models. If you get into problems get too complex, we can't handle them. We can handle them, they're just beyond us. We need supercomputers. We need things to handle when we get more than a couple masses, things get crazy. So it's good to know that we can simplify a huge, crazy system of all these atoms in like a car and treat it as if all of its mass is at the center of mass of the car. That's super important. So how do we do this? And we're going to do this. I'm going to show you how to do this with a few easy systems. And then we're going to talk about what happens when we try to generalize it to something harder. But we're not going to do it. And you'll see why in a minute. So single particle, we apply a force. That force is applied as if the particle was at a point wherever that particle happened to be. The particle just has its own mass. Not too hard, right? But what about if we had two masses and they were connected by some specific or some massless rod or rope or something where they were always going to be at that distance away from each other, okay? And if these were equal, so if M1 equaled M2, you could tell me right away that their center of mass is right in the middle. One way to think about the center of mass is if you were to hold them up on, like if you were to make, you know, like a fulcrum, like a seesaw, and you put it at the center, it would balance. And if you put it anywhere else, one side or the other would fall. If M2 is bigger than M1, you actually need to move closer. And we're going to see that when we do torque. But for now, all we're interested in is the center of mass. And that's where you would put this fulcrum so that the two masses would be balanced and nothing would happen. That's the center of mass. It also can be done in multiple dimensions, and we'll talk about that soon. But instead of two, what if there were three? And these distances weren't equal and these masses weren't equal. We might not be able to figure out where, other than trial and error, where that center of mass is. But I should say where this center of mass is. If I apply a force, they both move up, right? If I apply a force upward at the center of mass, the whole thing moves. If I apply a force at the center of mass, everything moves with that. You treat them as if they're all being acted on by the same net acceleration. Okay, that's important. So in a way, we treat these as rigid bodies. And things get a little weird or much harder when things aren't rigid bodies. So we're just going to imagine that these are rigid bodies and they're uniform density, meaning the mass is distributed the same way in every direction. So here I want to talk about where the center of mass is on these shapes. And I don't want you to try to do math. What I want you to do is what you know, what you've probably known as a child, how to balance things. If I have a cube and I want to balance the cube, I can balance a cube on any face, right? As long as I'm at the center of the face. The center of mass of a cube is right in the middle. It's in the middle of the cube. It's at the center. And you can treat a cube or a block as if it's a point particle really easily. That's why we use them in the free body diagram stuff. We imagine everything as a block because humans understand that a block is essentially an object that will travel on a flat surface and its center of mass is at the center. Okay. And the reason why we don't use spheres is because they roll, actually. And we're going to talk about rolling soon, but a sphere, I can put my fulcrum anywhere at any point. A uniform sphere, the center of mass is at the center. It is precisely at the center, and if this is a perfect sphere, it is at the center of that sphere. A rod is a little bit more difficult. If it weren't uniform, we wouldn't know where it was. But a rod, we just say, is right in the center. And by rod, we really mean that it has no depth, right? Even though we would draw it like this, we assume that it's basically completely thin. It's like a two-dimensional object. It has some height and it has some length, but it doesn't necessarily have any width. It may not even have some height. It may only have the length. The long, thin rod is right at the center of the rod. If I were to try, however, to balance this thing on my finger along the edge, we know that it would be directly in the center of the rod, right? If you were trying to balance your pen on your finger, your pen, you should be able to just put your finger at the center and hold it there, right? Finally, though, we have a top. And a top, I mean a child's toy that spins on its edge. Now, if this thing were upside down, you know that you can just put it over the center, right? So this thing has a center of mass that lies directly at the center, but we don't know how high up or down it goes. We know it's at the center, aligned with the tip, but we don't know where it actually is. So what this should lead you to understand is a few things. Something called symmetry. And symmetry we'll talk about much later, or we'll talk about soon, but symmetry says that as long as the mass distribution is the same in the positive and negative to the right or left of a certain axis, then you can treat it as if right in the center, that's the same. And what I mean by that is, if I have a triangle, I know that the center of mass is here. I don't know how high it is, but I know it's here because if I look to the left or I look to the right, the triangle looks the same, right? Same here. If this were actually truly in the center, it looks a little off to me. If I look to the right or I look to the left, I see a mirror image. And if I look up or I look down, I see a mirror image. So I know that this thing's right at the center there. There's symmetry. If I go along this y-axis, the top looks the same to the right or left, or even back or forth. But when I go down, if I put a point here, it's not symmetric up and down from this point. So I know where it is along this axis, right? But I don't know where it is necessarily along that axis. Symmetry is super useful because we don't have to do the math if we know from symmetry where the center of mass is in one direction. And the center of mass, I should have said, is really x, y, and z, right? And we write x COM, y COM, and z COM. And you can find each of those separately. And that'll give you the coordinates of your center of mass. Obviously, this is a little bit hard because you always have to figure out where your origin is so that you can start measuring. That's usually somewhat obvious because you could start from an end, or you could start at the center, or you could start wherever and figure out what your origin is. But for solid objects, you know, usually you have symmetry, and that tells you where to place your origin and where to start. For example, this triangle here, I would say that this point is x, y is 0, 0, right? And then I could measure up from y, and whether I went negative or positive x, it wouldn't matter because I would get the same mass. And you'll see why that all cancels in a second. But so symmetry is cool. We'll use it in a minute when we try to find the center mass of a triangle, and you'll see how this works. And then we'll talk more about it. But mathematically, what we get is that m times x, where this is the net m, and x is where the center mass is equal to m times x for every single mass in our system, right? So let's say this is 1, and this is 2, and this is 3, and so on and so forth. So no matter how many masses we have, we take the individual distance in one dimension to each mass, and these x's can be positive or negative, and we'll see that in a second. But we add all these up. We then divide by the sum of the masses, and that tells us where our center mass is. We do that for x, we do it for y, we do it for z, whatever directions we care about, however many dimensions there are in the problem. So 3 masses in one dimension. As I said, I'm going to have to choose an origin. Let's say that M1 is 1 kilogram, and M2 is 2 kilograms, and M3 is 3 kilograms. And furthermore, let's say this guy is located at 5 meters, this guy is located at 10 meters, and this guy is located at 15 meters. And we want to know where our center of mass is, right, for the system. Now, obviously, the center of mass is only going to be in the x. This is x, this is y. Can only be in the x direction because all of our masses are only in the x direction. But where is it? So going back to here, we have the sum of our masses. Well, we have x COM is equal to m1 times x1. That's 1 times 5, plus m2 times x2, which is 2 times 10, plus m3 times x3, and this is the sum of 1 plus 2 plus 3. Now this is 5 plus 20 plus 45, which is 70, over 6. So 70 divided by 6, and that gives me 11.7 meters. So that means my center of mass for these 3 guys, these 3 masses act as if they are a 6 kilogram mass located at 11.7 meters from the origin. That's super, super easy. I think it's some algebra. We're going to do a triangle in a minute where we have to do y as well to figure out what x and y are. But this is it. This is all you have to do, as long as you only have point masses. If these things become infinite masses, like a rod is actually an infinite mass, you have to do the full integral on it or use symmetry. And we're not going to do those ugly, horrible integrals. If you've done them already, if you've done solids of revolution, if you've done moments, right, you'll figure out that these integrals are awful. Particularly for really weird shapes, these integrals get crazy bad. I don't like these integrals at all. And when you have symmetry, it actually makes the problem easy. So what we're in general going to need to know is, in general, we're going to have this case here. where we'll have 3. And it might be a rod attached to 2 masses, right? And we could say that this rod is actually at 10 meters. So the center of this rod is at 10 meters, and mass 1 is 5 meters away this way. So this guy's at 5 and this guy's at 15. And what we would see is that the whole system acts like the center of mass is right here. Okay, that actually will come up. We're going to do this all again when we talk about equilibrium problems in chapter 12. That's going to be the last thing we do before we have our next exam. So this stuff will come back. But for now, what I want you to know is I want you to be aware of it for 2 reasons. 1, we're going to need it for chapter 12. But 2, this exact formulation, this exact mathematical idea is what you're going to have to do in 4B for electrostatics. If you need to find the potential of a charge, you have to sum up all the potentials of the other charges to figure it out. So you end up doing essentially the same architecture of the equations, except there you're solving for potentials, which means that you're not looking at mx, you're looking at a potential of a charge. So you're going to have to know how to do this. And essentially this is just like a weighted average, right? It's the weighted average in the x direction of the system, and in the y direction, and in the z. And if that helps you, I hope that helps you, that you're basically finding a weighted average. Pretty easy, right? I should also note that if we move the origin, let's say we move the origin, something occurred to me. Let's say that I move the origin to right on top of mass 2. So now, right, my mass 2, my mass 1, and my mass 3. Except now these guys are right at the origin. So this is now at -5, 2 is at 0, and 3 is at 5. And again, they're still 1, 2, and 3 kilograms. So 1 kilogram, 2 kilograms, and 3 kilograms. So where is the center of mass? So the x center of mass is 1 times -5 plus 2 times 0 plus 3 times 5 over, again, 1 plus 2 plus 3. And what I get is I get -5 plus 0 plus 15 is 10, right? So 15 minus 5 is 10 over 6. And 10/6 is, what, 11 or 1.6? 1.67. So 1.67 meters. Positive. That means it's 1.67 meters to the right of mass 2, which is exactly what we found here. It was at 11.7 meters, 2 was at 10 meters. So it was 1.7 meters to the right. You'll always get the same center of mass, and sometimes it's helpful to take your origin around one of your masses so that you don't have to multiply by it. That's always helpful. When you do that, though, you have to make sure that you compute your x distances from your origin. Here, we computed them from x is 0, so this was 5 away, this was 10 away, this was 15 away. Here, we put the origin at the mass 2, so this was -5 and this was 5. I hope that makes some kind of sense. We'll actually do that quite often. So in a sense, you have 2 tricks you can use, and that's that you can choose your origin wherever you want, and it eliminates sometimes your masses, and you can use symmetry or symmetry. So let's talk about 3 masses, and we'll do it the 2 ways. So this is at 2.5 meters, this one's at 5 meters, and this is at 7 meters in the x. Each of these are 2 kilograms. So mass 1, mass 2, and mass 3, they're all 2 kilograms. So I want to figure out what the center of mass is of this triangle of masses. I want to figure out where it is. So I need to do x and y. X center of mass and y center of mass. And these two, this is m times x for each one of them. This is m times y for each one of them. And I'm going to put a big M with little feet on it. That's the sum of my masses. Sum of my masses is m1 plus m2 plus m3. They're all 2 kilograms, so their big M is 6 in this case. 6 kilograms. Okay, so let's try and figure out x mathematically. We know that x1 is 0, right? Mass 1 is at 0. x2 is 2.5, and x3 is at 5. So we have that the x center of mass is 0, well, 2 times 0, plus 2 times 2.5, plus 2 times 5, over 2 plus 2 plus 2 over 6. This is 0, this is 5, this is 10, right? Why does that look a little bit off? What have I got wrong here? 5, 15. Because this should be right at 0, or I mean right at 2.5. I'm sorry, my brain isn't working. 15 divided by 6 is 2.5. Now, how did I know that this was 2.5, that this had to be 2.5 in the x-hat direction? Well, I knew because of symmetry. In the x direction, we have two masses that are separated by 5 meters, and right on the center of those is my third mass. So in the x direction, I have, if I move 2 down here, so that I'm only considering the x direction, I just moved it down, I can see that there's symmetry. If I look to the right of 2 and I look to the left of 2, the whole system looks the same in the x direction. And therefore, wherever the symmetry axis is, that's where your center of mass is. However, in the y, things are a little bit more complicated. And that's because y1 is 0, y2 is 7, and y3 is 0. So we see that y center of mass is 2 times 0 for mass 1, sorry, plus 2 times 7 for mass 2, plus 2 times 0 for mass 3, all over 6. This is 14/6, which is 7/3. That's 2.3. So 7/3 is 2.33. 2.33 meters in the y-hat direction. So that tells me that at the point 2.5 and 2.3, my center of mass, right, is at 2.5 and 2.33. And this triangular system actually moves as if all of its mass were there. Now, I could also understand this in a weird way by noting that I could find this geometrically, or if I can draw a straight line. I have the worst time drawing a straight line. So imagine this triangle, right? You could draw a line like that, you could draw a line straight down, and you could draw a line like that. And where they all intersect, if I had drawn those well, that would be where the center of mass is, because there's symmetry on either side of each of these axis lines. And so where they all converge would be my center of mass. That's another way to use symmetry. All these tools are basically to keep you from having to write this for y and z and x, you know. So symmetry is super easy. We don't have to do the symmetry or the x direction here because we knew that the x direction, that the center of mass had to lie along 2.5. We only had to find the y. And if I ever ask you to find the center of mass, all you have to do is figure out where your symmetry is, and you don't have to do those parts. You can say, I know from symmetry, x is at 2.5 for the center of mass. The center of mass x is 2.5. If I had a solid, like a cylinder or something, And you might be wondering, well, how do I integrate for a solid? What you end up doing is you use this integral, and you actually use that P is dmdv if it's uniform. Solve this for that, and you get x rho dv is over rho dv, where rho is the uniform density. Do those integrals, and that tells you where the x is. We won't be doing any of that, but you probably did it in calculus. I guarantee you did it in calculus. The problem is that, again, I want to teach you physics. I don't want to teach you math. And we can learn the physics for solid uniform objects without worrying about finding our center of mass from some elegant mathematical equation. That's not to say that you don't want to learn how to do it, particularly if you're an engineer. Go back to your calculus and learn how to integrate the center of mass of a solid doing integrals. It's important for when you don't know. And what I mean by you don't know is, imagine you have something that's like a top with a cylinder through it, and you wanted to find the center of mass of this weird spinning top thing for an engineering problem that you have. To do that, you're going to have to integrate through that. I mean, there's actually symmetry here, but I have no idea along the y-axis where the center of mass is. I know the x and z are going to be, meaning the x and z, if the x and z are essentially like in this direction, and the y is up. I don't know where along the y the center of mass is. Just like with the triangle, I would have to integrate along y, and that's actually kind of a pain to do, to try and do correctly. We won't do that. If you need to know, I'll give it to you. Most often what we're going to have to use is we'll have rods or scaffolds or planks, and you'll have to be able to know that right at the center is where the center of mass is. And that's for way later. That's for when we're doing torque. We'll go through and we'll talk about this all over again when we're doing torque. If it's a ball or a block or a cube, it's at the center, right? You should know where the center of those two things are, of a rod and a sphere. The reason why is gravity is going to act at the center of mass. And when we have to find torques, we're going to have to account for that weight acting on the center of mass. We'll get there, but for now, one thing I do want you to do is, in the book, there's a really cool example of a disc, right? And what you can realize is that the center of mass of two objects, right? The total center mass is the center mass of two objects. So really, when we're talking about two masses, we're saying this one's center mass is here and this center mass is here. And what we're saying is that the center mass is equal to the center mass of one plus the center mass of two, where this is the sum of their masses times x, right? For one and two. That means if we had like a disc and we took out a smaller part, well, we would know that the center mass of this side and the center mass of this side is equal to the total center mass. That problem's pretty cool. It's an example. If you don't want to do it, cool, don't do it. If you want to do it, check it out. It's a pretty nice problem. It's one of the few problems in our book that I actually really do like, because it teaches you a concept. And that concept is that for multiple solid, if you find the center mass of this little top part and the center mass of the bottom part, and you add those two center masses, you'll get the center mass of the entire thing. That's weird. That is a really weird idea that helps us out so much. We're going to talk about that later, but essentially a lot of things like the force of gravity, you can just add them all together. It's super helpful. You can treat them as if they're individual components and they don't affect each other. We'll talk about that when we get there. So far in this lecture, we talked about center of mass and we introduced momentum. Like I said, just know how to find the center of mass from this equation in the X and Y directions. As long as you understand this and you understand these two examples that I did for you pretty well, you could find the center of mass of a triangle. You could find the center of mass of 3 or more. It could be 30 of these guys. You could find that center of mass, then you're fine. You've got this down, and that's all I want you to know. So now we're going to move on and actually start using momentum to do problems. And like I said, the fun thing is we're going to be able to do real stuff, actual stuff. And I'm going to try to remember to talk about car accidents at the end of this little part, because I forgot that I wanted to talk about that, but I totally want to talk about that with you. Okay, so impulse. What impulse is impulse is force times the time that the force is applied. And what that ends up being is the change in momentum. What that's saying is, if I push you for 5 seconds with a constant force, your momentum changes, your MB changes because your velocity changes, right? And if the force is in the same direction or in whatever direction, you'll speed up in that direction. So unlike energy, where we talked about work and work depended on the displacement, this doesn't depend at all on the displacement. It just depends on the time, right? The momentum change only depends on the angle or the direction of the force and time. There's none of that positive and negative work. We don't say a positive impulse or a negative impulse. We just say an impulse. But the net change in the momentum is due to a force. And how we do this simply in an integral is we take a force and we assume this is constant. So we just get this integral just becomes T initial or T final minus T initial. Assuming T initial is 0, we can choose to start measuring time whenever we want. We get force times time. The integral of dP is just P final minus P initial, which is this. So how does it work? How does it work in the real world? Well, I hope I had this happen before. People don't know what baseball is. In baseball, someone throws a ball towards another person. That person has a bat, and they swing the bat, they hit the ball, and the ball shoots into the air, and if it goes outside the park, they get a home run. They try around bases. So what I'm saying in this example, though, is I have a 5 kilogram baseball, and I've thrown it level to the ground in the X, and you've got to assume that it can travel in the X direction. Its velocity is 40 meters per second, and this is my 0.5 kilogram mass, okay? But I need to call this negative, or I'll have to call the final velocity negative. I could flip this whole thing left or right, doesn't matter, but this guy's negative. Do not forget the negative sign. That is the big warning. This is what people mess these problems up with. They forget that the incoming velocity in this case would be negative, and then they get the wrong answer. So if the ball's coming in and the batter hits it, the batter applies a force for some time, and that time is 0.5 seconds. And what happens is the ball goes the other way now with a final velocity of 45 meters per second. And what I want to know is what's the initial momentum, what's the final momentum, and then how much force was applied by the batter. So this is pretty easy. We know that the mass was half kilogram. We know the initial velocity as it came towards the batter was 40 meters per second negative. After, when it's leaving, it's doing 45 meters per second positive. And the time of the collision, the time of the impulse, was 0.5 seconds. That means the batter applied a constant force for 5 seconds. So our impulse equation, remember, is force times time is the change in momentum. MB final minus MB initial. what is MV final? What is MV initial? MV initial is just the mass, 0.5 times the initial, negative 40. This is negative 20 kilogram meters per second. We have that done here. This is 0.5 times 45, which is 22.5 positive momentum, kilogram meters per second. That was the first two questions I wanted to know. I just want to know what its initial income. So it was coming towards the right, or from the right to the left, with negative 20 momentum. Its momentum had to be changed so that its momentum was now going from left to right at 22.5 kilogram meters per second. That's a big change. That's a major change. Mathematically, how we do it is we just plug these in. This is, 22.5. This is minus 20. Remember I said just a minute ago, don't screw up your signs. Why is this a minus? Because the batter had to stop the momentum that was going from right to left and give it the momentum going from left to right. So the force times time, the impulse, had to supply enough momentum to stop the incoming momentum and impart or give it the outgoing momentum. So that ends up that these two things are going to add together. And what we get is FT is 2.5 plus 20, 42.5. To find the force, I simply divide this by time. This was kilogram meters per second. If I divide by time, this becomes kilogram meters per second squared. The time was 0.5. That's a half, so double that. And I get 85 newtons. So the batter had to apply a constant force of 85 newtons for half a second in order to change the momentum of the baseball and give it a final velocity of 45 meters per second. That, if you watch, I don't know, high school baseball maybe, or maybe junior high school baseball, that's about what you'll see. That's a ball that's doing around 80 miles an hour, maybe 84 miles an hour, gets hit and it's doing 90 when it leaves. So probably high school, right? Maybe some college. But yeah, that's all we're looking at here is we changed the momentum because we applied a force for some time. Now, for those of you who know sports, you probably know that in golf, in baseball, you're always told to follow through. What does follow through mean? Follow through means you want to extend the time that the baseball and the bat are in contact, or your foot is in contact with the soccer ball, or your golf club is in contact with the golf ball. That's because if you increase the momentum or you increase the impulse, you increase the time, the impulse increases. The impulse increases, meaning there's an increase in the change in momentum of the ball, right? So the greater the increase in, well, the greater the impulse, the greater the increase in momentum. You may not be able to get more force out of your muscles because your muscles are only going to be able to apply the force that you can, but you could always apply more time, and that's what you get for following through. Now, follow through means that we increase the time. So let's talk about this. If we assume you can hit that ball with 85 newtons of force, but now we make sure that you follow through and you extend the time from half a second to 0.8 of a second. We want to know what the final velocity of the baseball would be. Treat the incoming velocity still is minus 40 meters per second, and therefore the incoming momentum, the initial momentum, was a half times negative 40 meters per second in kilograms. So this is negative 20 kilogram meters per second. That's still the same. Your force times time, your impulse, is 85 times 0.8. And from this equation, if we want to find what V final is, move this over. So we get force times time, impulse, plus mv initial, and then divide by m. And we see that we get 85 times 0.8 plus negative 20, all divided by 0.5, and we get 96 meters per second. Remember before we were getting 45? We doubled it, but we only increased the time from 0.5 to 0.8. We more than doubled the final momentum just by doing that, by applying a bigger impulse onto the ball. We changed the momentum much, much greater. The other side of that, and like I said, for those of you who don't know baseball, I'm sorry. In baseball, one thing that people will do is they'll bunt. And what bunting is as the pitch comes in, they hold the bat straight and they let the pitch hit the bat and bounce off. And it just kind of dribbles in front of them. And if you do that right, you make it so that it's hard for either the pitcher or the catcher to run over and get to the ball. Give you a few extra seconds to get to the base. For us, what that means, what I mean by bunting is you decrease the impulse time. So you decrease how long the bat and the ball are in contact. What this would be like is you just kind of let the ball hit the bat and it just goes dink, and that's it. It just bounces right off. So if we decreased the time of our impulse to 0.2, I don't know what this doubled means here. It shouldn't say doubled, I'm sorry. This should really say decreased, typo, to 0.2 seconds. What is the final velocity now? And so again, our initial was 0.5 times minus 40, so minus 20 kilogram meters per second. And now our force times time is 85 times 0.2. If I multiply that, that's 170 times 0.1, which is 17. This is only 17 Newton seconds, right? If I did that correctly. So 17 plus negative 20, if I solve for V final, divided by a half, gives me negative 6 meters per second. And what does that mean? That means the ball goes behind me and keeps going from right to left. That's because that impulse, that force times time, wasn't enough to completely overcome the incoming momentum. It comes through, and I ding it with the bat. Comes through, the bat hits it, and now it has a little bit of momentum continuing in that direction. So the bat slowed it down, but it didn't stop it. It wasn't able to change its momentum. Another thing, much like when we do free body diagrams, when we talk about the momentum and impulse, we don't care about what caused the impulse. We only care about the change in momentum to the object that the impulse acted upon. So I'm going to talk in a minute about, we can find the momentum and the impulse in each direction and then add them. So you could have something coming in at an angle, right? And hitting, so some force that comes in at an angle. You can apply a force at 30 degrees, let's say, for 4 seconds, 300 Newton force at 30 degrees for 4 seconds. You could find the change in momentum in the X and the change in momentum in the Y, and then figure out what the total momentum is using P is PX final squared plus PY. That's easy enough to understand, right? We've done that enough, and figure out what direction it's in from the angle is arctan of X over or Y over X, all that good stuff. We've done that. I don't need to go over that. What I do need to go over, however, is a kind of weird problem. And unfortunately, this is another baseball problem. But it's an interesting one. And if you understand it, you'll understand momentum. So again, we have a half kilogram baseball coming in at negative 20 meters per second to a batter. He swings, and his swing is at, the force is at 60 degrees, and the ball goes straight up in the air. So after the bat hits it, it only has VY final. Vx final is 0 after the ball is hit. And so what we need to know is what is the final velocity after the collision and how high does it travel? So visualizing this, we can visualize this as vectors, which is actually pretty nice. The initial momentum, remember, of the ball is m v initial, but v initial was negative 20 meters per second. That means this is 0.5 times negative 20, and we get negative 10 meters per second in the negative x direction, x hat. What is the initial momentum in the y? 0. So P initial is along the x-axis, facing negative is negative 10. Then if we add our impulse, which is our force times time, we know this is at 60 degrees. So if I add this at 60 degrees, did I give you, I didn't give you what the force was, but I gave you that the time was 0.4 seconds. So this is our impulse. And our final vector is v naught of y. I'm sorry, v final of y. And you can see that there's no, this is our p final because there's no v final of x. And so we end up with this vector diagram that we can add these things together. That means that we could add p initial plus I is equal to p final. Our p initial was m v initial of x. Our I was our force in the x times t plus our force in the y times t. And if we put little I hats, right? And our p final is what? Well, we can see that this would be m v naught x plus fx t in the I hat plus fy times t in the j hat is equal to p final. This stuff is equal to 0. There is no I hat final. P final, therefore, is simply going to be fy times t is equal to m v final in the y direction. And these are in the j hat direction. If you didn't follow that, we're going to do it again in a second. But what I want to show you is that's a fancy way of stating that as the ball came in, the batter hit it with enough momentum to just cancel the momentum that it had going from right to left. And he gave it enough momentum to go up in the y, to head upward in the y. So the force times time, the impulse had to be in the x, the impulse in the x had to equal the positive or the opposite of the initial momentum. The impulse in the y had to equal p final. I hope that makes sense to you. And we'll see that mathematically right now. Okay, so the impulse is f times t, but this is actually fx times t in the I hat plus fy times t in the j hat. This is why we use these vectors, these unit vectors. We know that fx is f cos theta, and we know what theta is, times t. And we know that fy is f sine theta times t. Now, in order to find this force, okay, and we found that, or we were told that t was 4 seconds, 0.4 seconds. We know that p final is only in the j hat direction. It would be px final I hat plus p y final j hat, but there's no velocity in the x after the collision. So we know this has to be true, right? If this is true, if px final is equal to 0, px final is equal to p initial x plus I in the x, right? Which is, I of the x is fx times t. We've already got that, right? This is our I. Okay, and p initial of the x, it's just v, mv initial in the x plus fx times t, and that's equal to 0. So plugging stuff in, we know that this is going to be 0, or I mean negative. So this is Fy of t, right? With a negative sign if I move this over. M was 0.5, this was negative 20, so negative negative 20. This gives me a positive, sorry, Fx. This is F cos theta times t. I know theta is 60 and I know t is 0.4. So I'm going to move up for clarity. 0.5 is, that's a 10. So this would be, F would be 0.5 times 20 divided by cosine of 60 times 0.4. Just take this and divide both sides by it. I get 10 over 0.4, sorry, 10 divided by 4 times cosine of 60, which is 2. So this is 5 newtons. The magnitude of the force was only 5 newtons. Okay. What is the final velocity now? Knowing that, what's the final velocity? Well, that's easy because the force in the x times t, I'm sorry, force in the y times t is equal to F sine theta times t, and the final momentum is the impulse, right? Which is equal to mv final of y, and this is mv final of y. So what I get is I get 0.5 times 5, right? Sorry, let me take that back for a second. Just to be clear. So my impulse is Fy times t, and that's equal to mv final of y. So to find v final of y, I would need to take Fy times t and divide by m, which is F sine theta times t over m. T, remember, is 0.4, m is 0.5, F is 5 newtons, and theta is 60. So let's do that real fast. 5 sine of 60 times 0.4 is 1.7 divided by 1.5 is 1.15, 0.15 meters per second, which seems a little weird, but I feel like something's weirdly wrong here. The initial momentum in the x was m v naught in the x, which was 0.5 times minus 20, which was 10 kilogram meters per second. And if F sine theta is 10, right? Oh, I'm sorry. F sine times t is 10. Then I get F is 10 sine theta over t. T is 0.4, sine of 60 is a half. So sine of 60, no, it's sorry, it's 0.866 times 0.4, so 10 divided by this answer is 28. Yeah, where did I mess that up at? Oh, no, I'm dumb. Forget what I'm doing. I did do this right. So F cos theta times t is mv x initial, right? This is 10. It's a negative 10, but that's okay. It has to be equal to that. So it's magnitude of it. So the force required would be cos 60 times 0.4 is equal to 10. 10 divided by 0.4 times cos of 60, and cos of 60 is a half, is 50. That seems more right. Yeah, so I knew something was iffy wrong here. 50 newtons. So when we go back here, this, I messed up my calculator. Yeah, that should have been 10 over that is 50 newtons. And okay, now, if I know that the force is 50 newtons, plugging that in gives me that 50 sine of 60 times 0.4 is 17.32 divided by 0.5 gives me 34.64 meters per second. That's right. So my V final and my Y is 34.64 meters per second. What is the max height? And here, this is why we learned all those constant acceleration equations. This just becomes one-dimensional projectile motion or free fall, whichever way you want to call it. V final squared minus V initial squared is equal to minus 2G Y final minus Y initial. But be careful, because this is now your V initial. Your V initial of this motion is the final velocity that it left with. And I really shouldn't draw it this way. I should really draw it up to max height. So V initial here is equal to V final Y, and V final here is 0. And Y final is H, and Y initial we can say is 0. So this goes away, this goes away, this becomes H. The negative sign cancels, and we get that H is V initial squared over 2G, which is V final Y squared over 2G. Now 34.64 times itself is 1200 divided by 2 times 9.81 is 61.2 meters. Okay. The only trick here, well, obviously there's the trick of the initial momentum in the X had to be completely canceled, but that only happened because of the way we stated this problem. That only happened because I told you that after the collision, the only momentum was in the Y. And you knew that because the velocity was only in the Y. Therefore, the momentum was only in the Y. You could have done this several ways. You could have looked at it like this and solved these, setting this side equal to 0 and setting this, the Y equal to that, and figured stuff out from there, which is essentially what we did. We just did it with this equation, that I was Ft, which meant that it had an I component and a J component of f of xt and f of yt, where f of x, much like in projectile motion, is f cosine and f sine times t. That's the impulse in the x and the impulse in the y. The impulse in the x had to be equal to the initial momentum, and the impulse in the y had to be equal to the final momentum. And from there, it's just making sure that you don't make a calculator error like I did. So once you find your final velocity, you find the force, you find the final velocity, and then you can find the time, or I mean the height going up. So the force in the y was F sine theta, where F was 50 times sine of 60. All that good stuff. The final velocity in the y was F final y, V final y, is F of y times t over m, where this was F sine theta times t over m. And that, once you have that, that becomes the B initial for a constant acceleration equation. Okay? Other than that, I actually really like this problem because it's tricky, and it's a good way to make sure that you understand how momentum in the x and the y are completely separate things, right? Before we move on to collisions, I want to talk about something that I forgot to put on here. And what that is I want to talk about your car. And so some of you may not realize a few things about cars. So we're going to talk about how a car keeps you safe, right? So imagine you're driving in your car and you're doing 30 meters per second, right? And you hit a wall and stop. So V final is 0, and you do this in 1.1 seconds. The whole collision lasts 1.1 seconds. What is the force on your body if that happens? So we have F times T is mv final minus mv initial. And your car, let's say, weighs 1,400 kilograms. I don't know what it weighs, but let's just use this number, okay? Since V final is 0, what we get is that the force acting on the car is mv initial with a minus sign over t. That is 1,400 minus sign times 30 divided by 1.1. If I put that in my calculator, 1,400 times 30 divided by 1.1 is about 38,000 newtons. 38,000 newtons. And if I divide that by 1,400, that's an acceleration of 27 meters per second squared, because this force, right, is ma. So if I divide by the mass, I get an acceleration of 27.3 meters per second squared. That's 3 Gs, okay? That's probably survivable, but you might get hurt. That's like falling at 3 times the normal acceleration. That's pretty crazy. I mean, yeah, race car drivers will see like really high Gs on themselves, high amounts, high multiples of 9.81. As you launch into space and as an astronaut, you might pull 30 Gs. Stuntmen can pull 30 Gs and survive. But it really starts to get dicey if you get too high up. Even a 10 G can kill you. So one thing you probably never thought about, or maybe you have, and if you have, great, but the seatbelt in your car, okay? What is the seatbelt in your car designed to do? Well, it's actually designed to do 2 things. Some people think that all they do is they hold you in place so you don't fly out of the car in the event of a collision. Well, yes, that's true. But seatbelts also do something else, and they do it in conjunction with an airbag. An airbag, some people think, is a pillow, which is a nice place for you to crash into, a soft place for you to crash into in the event of a crash. And that's not what an airbag does. What an airbag and a seatbelt do for you, some of the things they do for you, probably the most important things they do for you, is that they create a longer time for your collision, because as you are sitting down, right, in your thing, as this airbag blows up, it immediately deflates. So as you're crashing through it, it's deflating. What it's doing is it's making the time become longer of the collision and your body. What we're doing is we're increasing T. And effectively, if we could increase T by half, so this becomes 1.7 seconds, what is the force on you now? Well, 1,400 times 30 divided by 1.7 is only 24.7 thousand newtons, right? And again, if I divide by 1,400 kilograms, that decreases my acceleration to 17.64, which is about 2 Gs. So by extending the time of the impulse acting on your body by the force of the collision, we actually make the impulse longer, and we decrease the acceleration on your body. We make it so that the change in momentum happens over a longer time, and that decreases the acceleration that we need to have on you. Another idea that we have here, in modern cars, I used to drive a 69 Pontiac Valiant, Plymouth Valiant, and that car was like an old fridge. It was a thick piece of metal that had no give. If it hit something, the whole car hit. Your car today, my car today, I drive a Honda Accord, it's a 2019. If I hit something like, I don't know, something light even, that car's bumpers fly off, pieces of it go flying everywhere. Things are meant to just break and shatter. Why? Well, when this car hits the wall, today's Honda Accord, when it hits, a bunch of mass gets carried away. And let's say a third of the mass gets carried away. So with your seatbelt, we already found that M V naught over T was the force acting on you. And if we divide this by M, the acceleration acting on you was V naught T, right? Yeah. So let me not do that for a second. Let me leave this alone. Force is, and I really hate. So let's do this first. So let's say your 1,400 kilogram car now, when it hits, the mass is reduced by a third. And so the force is equal to the mass divided by 3, V naught over T. And as we said, this was what, 30? So this is M divided by 3 times 30 over T. The mass was reduced actually to 2/3 because a third of it flew away. So this would be 20 times the mass over T. And remember, M was 1,400 and T was 1.7, we said, with the seatbelts and everything else. Yeah. So we now get 30 divided by 3 is 10, so 20 times 1,400 divided by 1.7. We now get 16.5, 16,500 newtons is the force. If we divide by our initial mass, that's only 11.76, the acceleration meters per second squared. Now what's going on here is the pieces that fly away take momentum with them, okay? So the momentum involved in the collision ends up only being a third or 2/3. The mass involved, only 2/3 of the mass is now involved in the collision. The impulse only needs to stop 2/3 of the momentum of the car before the collision. The initial momentum is 1,400 kilograms times 30 meters per second. Because a third of the mass flies away, it only needs to change 2/3 mv naught. It only needs to bring that to 0. So the impulse that's supplied only needs to stop that much. That's super helpful. It's why Formula One cars are designed so that only the body of the car stays intact. It also helps with weight, surprisingly, but they're made to completely break apart like a car made of Legos. And they carry away all that momentum so it's not involved. So the impulse acting on the car is much, much, much less around the person driving. And that's what modern cars are designed to do. That's how they save your life. You might think that you want to be in a big steel truck if you're going to be in an accident. You don't. You want to be in a really nice modern car with airbags that's going to blow apart when it hits something and let all those pieces carry away the momentum so that you are subject to much less force. 11.76 meters per second squared, totally survivable. That's falling off your roof. Yeah, you might get hurt. Yeah, you could possibly die if something went tragically wrong. But 9 times out of 10, you're going to survive that crash. And you're going to survive it because we understand impulse. We understand that we can change the momentum that needs to be stopped of the car. We can change how much momentum the car has, or we can extend the impulse so that the acceleration decreases on your body, because the acceleration is the force. That's what hurts you. So you want to bring that acceleration down as much as possible. This is actually really important. I almost forgot to talk about it, but it's really cool, and it's all just impulse and momentum. And that's how it saves lives. So tell people about this. Especially you probably have friends. My best friend doesn't like to wear a seatbelt. And I'm like, man, dude, your seatbelt could be the difference between life and death, not from being thrown out of the car, but to how badly you're injured. And the reason is it slows down the change in impulse. It makes the time take longer, I should say. It's weird to talk about time, but it makes the impulse have to occur over a longer time, which makes a longer impulse, which means that the change of momentum is allowed to happen over a longer time, which reduces the forces on your body. And that's a great thing, right? Anyway, so speaking of horrible collisions, this part you probably had before if you've ever had physics. I'm going to go over this really fast. In fact, I'm going to do a little bit of an example, but it's not too major. I think you guys understand this. The only thing I have to highlight are the equations to use and when to use them. So essentially, when we talk about collisions, we talk about two kinds of collisions. And we always talk about like billiard balls. We talk about an elastic collision. If this is mass 1 and this is mass 2, mass 1 could be traveling towards mass 2. It would still be traveling towards mass 2, but mass 2 could be heading that way. They could be going head on, right? In this case, mass 1 would be having to be faster than mass 2, but you could have any of those situations. Again, you need to make sure that the velocity, that you have the right sign on it, that you pay attention to the fact that it's a vector, it can be positive or negative, both before and after. Always draw these, kind of sketch them for yourself and make sure that the numbers you're getting make sense. But collisions are usually just one-dimensional for us. And going to 2 dimensions is easy. You just do the y and you do the x separately. And then you look at what happens after. You'll see that in a minute though. So in an elastic collision, imagine 2 balls, 2 ceramic billiard balls or whatever they're made out of, and they hit each other and they bounce off completely. They just bounce off like they're made of rubber. That is called an elastic collision. And in an elastic collision, when the things bounce off each other, the momentum is conserved before and after the collision of both masses, and the kinetic energy, the total kinetic energy conserved. That would mean, and we'll see this in a minute, but if the 2 masses are equal and one of them's at rest and one's moving, the moving one hits the other one, they completely exchange momentum and kinetic energy. That only happens if they're both the same mass. We'll see that though. So elastic collisions, they bounce off, the kinetic energy conserved, the momentum is always conserved. In an inelastic collision, and I hate that, elastic makes sense, you know, they bounce. Inelastic, I wish they would call like stick together or sticky collision or something. But in an inelastic collision, the 2 masses hit. So this is elastic, right? In an elastic collision, 1 hits and bounces off, and 2 maybe goes that way depending on how big it is. In inelastic, what happens is mass 1 hits mass 2, and then together they both travel at the same velocity, stuck together, heading off in the direction that mass 1 was originally heading. The velocity changes, but so they stick together, momentum is conserved. However much momentum they had before, that's what they have afterwards. However, kinetic energy is not conserved. And it's not conserved because when they stick together, they lose energy to intermolecular forces to bind them together. They lose it to heat. They lose it to a lot of weird things. So in an inelastic collision, Ke not conserved. That's the big one. Okay, they lose energy. You can't solve for the initial kinetic energy and say that that's equal to the final. You can totally do that in a elastic collision. So let's talk about elastic collisions first. Now, I said at the beginning of this lecture that we really are talking about the system's momentum. So let's look at this side here. Initially, the momentum is mass 1 times V1 and mass 2 times V2. Make sure that you know that this is negative, right? So we get mass 1 V1 initial plus mass 2 V2 initial, although this could be a negative. You know, this could be positive or negative, this could be positive or negative. Just depends on how we set up our coordinates. I'm going to, in general, use X positive to the right. The final afterwards, so they come, mass 1 comes in from the left, mass 2 comes in from the right. They hit each other, they bounce off because it's elastic, and they head off in different directions afterwards. The total momentum afterwards, the final momentum, is momentum of mass 1 times V1 final plus mass 2 times V2 final. So the total momentum before is equal to the total momentum afterwards. That's always true. The difference between an elastic and an inelastic collision is the final momentum. The masses are added together in inelastic. Okay, so we do this, right? And let's look at it this way. If mass 1 and V1 initial was 10 meters per second, and V2 initial was -5 meters per second, and mass 1 is equal to mass 2, they're both 4 kilograms, right? The initial momentum, we know everything here. So afterwards, we know that V2 afterwards is going 10 meters per second, right? We need to know what V1 is doing. So V2 final is that. Well, before this would be, 4 times 10, 4 times 10, plus 4 times -5, and that has to be equal to that. So this is 40 minus 20, so this is 20 kilograms, so this is 20 kilogram meters per second. That's the initial momentum. The final momentum then is 4 times unknown plus 4 times 10. So this has to equal 20. And I have plus 40, so 4 is equal to 20 minus 40, or I shouldn't call it question mark. V1 final is 20 divided with a negative sign divided by 4, which is -5, right? V1 final. And we already knew that though, right? Because if V2 got the momentum of V1, then V1 had to end up with the final momentum equal to the initial momentum of mass 2. But you can use the conservation of momentum to understand how a system can change without any forces acting on it. Conservation of momentum doesn't mean that the momentum of the individual parts can't change. They can exchange momentum all over. Your body's doing a lot of weird stuff, but it's not moving, right? But all the internal parts can conserve momentum and exchange momentum between them as long as your body continues to stay still without moving. Your body is a system. If you're sitting in a chair not moving, is at rest. All the internal stuff can exchange its momentum and not affect how your body moves. So the second thing that we have here is we have the kinetic energy conserved. And we said that these were both 4 kilograms, but that number 1 was 10. V1 initial was 10 meters per second, and V2 initial was -5 meters per second. And if we look at this, we can see all these masses are the same. They're all divided by half. But V1 initial is 10 squared, right? And V2 initial is -5 squared. So this is 100 plus 25. This is 4/2 times 125. This is 150 joules of energy. On this side, 4/2 is 2. So 2 times these two quantities, but we know this was 10 squared and this was -5 squared as well. So that's 125, which is again, 250, which is again 250 joules. So you can check it for yourself, but the kinetic energy, completely conserved. It has to be conserved. So in effect, for an elastic collision, you have P initial is equal to P final, and KE initial, I guess I'm writing them with zeros, is equal to KE final. Always true for elastic collisions. Completely elastic is what we call them. Always true. Now, taking those two equations, though, taking these two equations together, and I urge you to do it sometime, but I'm not going to do it for you. I'm not going to do it for you. You can do this. Do it once in your life and don't ever do it again, because it's a lot of algebra. I'll tell you what I mean in a second. So take this equation right here and take this equation right here, and using the fact that if V2 initially is at rest, using those two equations, you can solve for these two equations. What you do is if this guy is at rest, you get M1, right, is V1 initial minus V1 final is equal to M2 V2 final. And so you can plug stuff in and solve for these equations. You can actually substitute this equation into this equation, assuming that this is 0, as long as M2 is initially at rest, and you get these. Now, why would we want to do that? You might think to yourself, well, yeah, that's great. I mean, it works as long as V2's at rest and M1's moving, but how often is it the case that only one of the two particles is moving and one of them's at rest initially? Remember back when we did relative motion? Remember, it was like 2 weeks ago. We can always come up with a frame of reference where V2 is at rest, or M2, I should say, is at rest. So if M2 is at rest in some frame of reference, and we can figure out what V1 is, V1 initial is, we can solve these equations in the rest frame where M2 is initially at rest. So it is actually useful. In practice, we'll just start in that rest frame. So imagine that M1 is traveling at 5 meters per second to the right, and M2 is initially at rest, right? I'm not going to put in masses, but let's say this is the case. What we want to know, so this is V1 initial and V2 initial is 0. What we want to know is once they collide, what is the final velocity of either one of them? And you can see that you can get that just by saying M1 minus M2 over M1 plus M2 times the initial velocity. So as long as you have mass 1, mass 2, and the initial velocity of mass 1, you just plug numbers in. I'm going to tell you there is one small trick that I'm going to talk about in a minute, but that's it. For V1, the final velocity of V1 is M1 minus M2, M1 plus M2, V1 initial. This also assumes that positive, if this number is positive, it's in the same direction as V1, right? So you could actually have it point that way, and if this number came, if V1 was pointing that way, then V1 final, if it's positive, would point the same way as V1 initial. That's not a huge deal, though. You should know that already. V2 final, you'll notice that the difference between these two equations is that here is M1 minus M2, and here it's 2M1. Other than that, they're exactly the same. You can memorize these. You can put them on a little note card and just leave it by you. But this is this is elastic M2 initially at rest, okay? That's the only time it applies. So if you see, if the question says there's two masses, M1 is initially moving to the right at some speed, M2 is at rest, they collide elastically. You're always looking for this. If you see it elastic or inelastic, you know immediately you're going to use those equations. But let's look at these a little bit more closely. So we have that V1 final is M1 minus M2 over M1 plus M2 is V1 initial. And V2 final is 2 times M1 over M1 plus M2 times V1 initial. So what happens if they're equal? if they are equal, what is V1, what is V2? If M1 equals M2, this becomes 0. And so M1 hits M2. M1 after the collision is at rest, and M2 is moving away at the same speed and with the same momentum that M1 initially had. That's what these are telling you. That V2 final, because if M1 is just equal to M, you have 2M over M plus M, which is also 2M. And you get that V2 final is V1 initial. That's super important. So that tells us, and you'll see this if you've ever played the game of pool, where you hit billiard balls around. Sometimes you'll hit it just right, and the ball that you hit, the cue ball, the white ball that you hit to hit the other balls, when it hits another ball, it'll stop dead, and the other ball will shoot away. Pool tables are really good for understanding collisions, but inelastic, if I told you that after the collision, M1 is at rest, that's the same thing as saying they have equal masses. That's the only real trick that can pop up in a test or a quiz problem, is that if you're told after the collision, M1 is at rest, you know the only way that can happen is if it's an elastic collision and if they had equal masses. That's it. It can't happen any other way. They have to be equal. So that's another way of saying they're equal masses, and you need to know that. That's one of those physics assumptions that you're not told, and you just need to figure that out, okay? You'll usually be asked, what are the masses? What is the mass if M1 is initially at rest, or is at rest after the collision? So I could tell you that V1 is initially 5 meters per second, V1 initial, and I could ask you, right, what is M1 and what is M2? If V1 final is 0 and V2 final is 1 meter per second, or is 5 meters per second, right? Could you find it? Well, no, you couldn't find it. You don't have enough information to find it. You would have to actually get something more. So it turns out what the more would be maybe some kind of other collision that happens afterwards. I believe I have a problem that has 3 masses. At first, mass 1 is moving and mass 2 and 3 are at rest. 1 hits 2 and stops moving. So you know 1 and 2 are equal masses. 2 hits 3 and they both move after that collision. So you know that 2 and 3 aren't equal. So you can find the mass and then find the mass and then find the mass. That's for down the road. Don't worry about that. All right, so the other thing I want to talk about is something called limiting cases. You should get used to doing this, particularly in physics, if you're not already used to doing this in any math class, any science math class, and that's to look at extremes. So in this extreme, the second extreme, M1 is much, 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 much greater than M2. M1's a bowling ball, M2 is a marble. So if M1 is much greater, then assume that M2 is equal to 0. And if M2 is 0, you see that we get M1 over M1, and V1 final is V1 initial. The bowling ball runs into the marble and keeps going without losing any speed or momentum. If M2 is essentially 0, then this becomes 2 times V1 initial. So, big old bowling ball traveling at 2 meters per second hits a marble that's initially at rest. Afterwards, the marble's moving at 4 meters per second, and the bowling ball's still only doing 2 meters per second. That occurs if M1 is much, much greater than M2. What do you think will happen if the reverse is true? If M1, the mass initially at rest, or I mean initially moving, is much, 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 much smaller than mass 2. Well, essentially, what we should have happen, right, is nothing. Nothing should happen to mass 2, the thing at rest, because it's so big that it doesn't get moved, right? If essentially M1 is equal to 0, Then if we look at V2, then essentially this is approximately 0, and it doesn't move. But what happens to M1? What happens to the marble when it hits the bowling ball? Well, you can see if M1 is 0, that we get negative M2 over M2, which is essentially negative V1 initial, which means after the collision, the marble just bounces off the bowling ball and heads back the other way. And that's it. That's all you need to know about elastic collisions. We will have elastic collisions where mass 2 is at rest. You just use these two equations to find the final velocity for mass 1 and mass 2. The only thing to really know is that there's a unique case where they're equal masses. And what happens in that case is if M2 is initially at rest, after the collision, M1 is at rest. And M2 is traveling with the velocity that M1 had. Because momentum is conserved, because kinetic energy is conserved. That's the other idea though, is because the kinetic energy is conserved, sometimes you'll be asked to find the kinetic energy after the collision. And what you would do there is you would find M1 V1 final squared over 2 plus M2 V2 final squared over 2 is a final. This is the final kinetic energy. This is the initial kinetic energy, right? So you can find it if you don't know it, if you didn't find it. But in general, you're just going to plug numbers in here and be done with it. It's not too hard. This part of it is just plugging numbers in as well, really, right? Not a lot to really worry too much about. So inelastic collisions, momentum is still conserved. But as we said, and here we're going to do the same thing. V1 initial is moving. V2 initial is 0. And then afterwards, they stick together, and they both head off with a V final. How we write that mathematically is M1 V1 initial plus M2 V2 initial. If this is 0, they're equal to M1 plus M2 times V final because they stick together. And so what you get is M1 V1 initial is equal to M1 plus M2 V final. And that gives us this equation, okay? But look, and you'll see that if initially the kinetic energy was M1 V1 initial squared over 2, right? And this is equal to M1 plus M2 times V final squared over 2. If I plug in M1 plus M2 divided by 2 times M1 squared over M1 plus M2 squared times V1 initial squared, right? This becomes M1 squared over M1 plus M2. And so if I take out times V1 initial squared, that's what this right side of this equation equals. If I compare that, right, I can see right away that if I compare this to M1 over 2 times V1 initial squared, cancel those, cancel 1, M, cancel an S, I get M1 over M1 plus M2, right? That is equal to 1. So that means that I basically get this weird ratio if I try to take the ratio between them. That tells me that they have to be, they can't be equal. You can't solve this, because if you try and solve this, you get M1 is equal to M1 plus M2. Move that over, and the only way that's true is if M2 is 0. So that equation is not true. They are not equal, right? So ignoring all that stuff that I just did to show you that the kinetic energy is not conserved, we can do it much easier with numbers. If you just put in numbers, imagine that mass 1 and mass 2 were 2. So if mass 1 and mass 2 are both 2 kilograms, and V1 initial was, I don't know, 4 meters per second, plugging that in, I get 2 times 4, right, is 8. And that's equal to 2 plus 2, so 4, and I don't know what V final is. So V final would be equal to 8 divided by 4, which is a half a meter, I'm sorry, 2 meters per second, okay? But the kinetic energy was mv1, m1 v1 squared over 2. That is, this is the initial kinetic energy, that is 2 times 4 squared over 2, or 16. The final kinetic energy is m1 plus m2 divided by 2 times v final squared. And this is 2 plus 2 is 4, so this is 2 times 2 squared, and this is 8. So the final kinetic energy is only 8 joules. The initial kinetic energy was 16 joules. That's the reason why I'm doing this, is to show you that the change in kinetic energy is -8, right? It lost 8 joules in the inelastic collision when it stuck together. So the kinetic energy is not conserved in inelastic collisions. The only equation that we have is this one. And then, of course, you know, kinetic energy is mv squared. So the final, you have to use m is the sum of m's in the final to determine. So really what you should note is this is m1 plus m2 v final squared over 2 minus m1 v1 initial squared over 2. That is the change in kinetic energy. And that will always be, always end up being a negative value, okay? It's always going to be a negative value. It has to be. All right. So as far as those go, pretty easy. After the collision, what's the final velocity of the combined masses? So we know that this is an inelastic collision because it says combined. And we know that mv1 initial was 20 meters per second, and we know what m1 and m2 are. So we have m1 times v1 initial is m1 plus m2 over v2 final. Well, I guess I should just say v final. This would be plus m2 v2 initial, but v2 initial is 0 because we're always going to assume that in these collisions, m2 is at rest unless we're told otherwise. So our final velocity is simply m1 v1 initial over m1 plus m2. m1 is 5, v initial is 20, so this is 100. m2 is 10 and 5 over 15. What is 100 divided by 15? 100 divided by 15 is 6.7 meters per second. And if we look at the kinetic energy, the initial kinetic energy was m1 v1 initial squared over 2. That is 5 times 20 squared over 2. 20 squared is 400, so this is 5 times 200. That's 1,000 joules. The kinetic energy final is m1 plus m2 divided by 2 times v final squared, or 15 over 2 times 6.7 squared. And 15 divided by 2 times 6.7 times 6.7 is around 337 joules. Let's just say 336 joules. It lost, the change in kinetic energy is the energy lost, kinetic energy final minus kinetic energy initial, 336 minus 1,000. And that ends up being 664 joules negative. So it lost 664 joules of energy sticking together. That's pretty crazy. But it should come as no surprise that it lost 2/3 of the energy when it collided with a mass that was 2/3 of their total energy together, right? If you think about that, you'll kind of understand what mass is and how mass affects velocity, right? Mass is inertia. It's harder to move a bigger mass. And when the system suddenly increases by a whole bunch, it increases by 3 times. The system went from 5 kilograms to 15 kilograms. Therefore, its momentum decreased to a third. That should kind of reveal, if you really think about it, what's going on with momentum and mass. Anyway, let's move on to the last 2 topics that I really want to talk about. I know it's getting long, but this problem is really cool. And then the next problem, I'm going to teach you how to be a rocket scientist. So bear with me and we'll be good. Ballistic pendulum is a cool momentum to kinetic energy problem. It is the canonical momentum kinetic energy. It's the link between momentum and kinetic energy, and you all need to know how to do it. In fact, we may have a lab on it. It is a wonderful experiment. It's totally useful for catching criminals. Well, okay, it's useful in ballistics. How it works is you have a wooden block with a mass of, let's say, 4 kilograms. So that's our block. And we have a bullet, and let's be careful. I'm going to call this M of the bullet, which is maybe 10 grams, right? But this bullet's traveling at, say, 240 meters per second. It strikes the block, buries itself in the block. You assume that this is an inelastic collision. And whatever momentum, because it's attached to this stretchless, massless rod, causes it to swing up, and you get some final height above where the bullet struck to where it ends up. Above from the center up. You can determine that height using energy. Okay? So there's 2 steps to this problem. Before the collision and right after the collision, you write the momentum. So step 1, momentum. And then right after the collision, you figure out for step 2, the energy at A and at B. We figure out the energy, right? And if we have an angle there, we'll figure out what the angle is too, okay? Assuming we're given the length, let's say the length is 1 meter, I don't really care. We're gonna wanna find that angle. So this is mass of the little bullet times V initial of the little bullet plus mass of the block times V of the block initially, right? This is 0. And then afterwards, they're together. So add the 2 masses together and V final. And the point here is to find V final. So if we find V final, what we get is mass of the little bullet times the velocity of the bullet over m plus m. And that you can see here would be 0.01 times 240 over 4.01. That is 0.01 times 240 divided by 4.01, whoops, 2.4 divided by 4.01 is 0.5985. So let's call it 0.599 meters per second, okay? All right, and let's actually call this mass now. I'm gonna call this mass the total mass. The sum of the masses that I'm gonna use from here on out is 4.01 kilograms, the mass of the block and the bullet together. In the energy part, right, and this is a good review on energy, if I have it here, and this is big M, some of them M's, and then it's up here, right, and these are connected, some of the M's. I want to know what H is. A and B, I just write down the energy and set them equal to each other. So the energy it can have, we're going to neglect any springs, is mgya plus mva squared over 2. And the energy at B is mgyb plus mvb squared over 2. And we're going to identify yb as h. And remember, we were told this length was 1 meter because we're going to want to find the angle. Setting EA equal to EB, And first of all, we're going to say that YA is 0. We're going to call this our 0 line. And therefore, YB is positive H. G is down, we're assuming. So our Y is positive up. We're also going to assume that when it reaches the top of this motion, it no longer has any velocity. Okay, so the kinetic energy all turns to potential here. So we can get rid of that, and we can get rid of that. And we get that MVA squared over 2 is equal to MGYB. Noticing that the masses cancel, we get that VA is square root of 2G times H, right? Or, since we actually know VA is V final squared is 2GH, or H is V final squared over 2G. And what does that give us? We said V final was 0.599. So 0.599 times 0.599 divided by 2 times 9.81 is 1.83 centimeters, or 0.0183 meters. That's how high it reaches. If we know the triangle, when we have this, right, with some angle, this length and this length are the same, okay? This, right, this distance here is, this distance is L cos theta. So this distance is L minus L cos theta. If that doesn't make sense to you, think about it like this. If I have some angle and this is L, and then if I let it come that way, this part here is L cos theta, and the whole thing is L. So this part right here is L minus L cos theta, which we're saying is H, okay? So L cos theta is L minus H. Move the H over, move that over. Divide by L, and cos theta is L minus H over L. Theta is then arc cosine of L minus H over L. We know that L is 1, so 1 minus 0.0183 divided by 1 is that. And arc cosine of this answer is 10.97 degrees. So almost 11 degrees is our angle. And if we look back here, if this is 1 meter, then, and this is 18 centimeters, that's really small. It's a really small deal, but is what it is. Okay, that's the ballistic pendulum. You can look it up. There's a million examples. You're going to get a homework problem on it. And we may do a lab on it. It's a pretty cool experiment. They use it in forensic labs to figure out how fast bullets travel. If you understand it, you understand how to do inelastic collisions where two things hit together and stick, okay? And then it's really good because we then have to go to energy. And any problem that I can get 2 topics out of, I love. I love those on the final. If I can turn a problem into 2 or 3 different topics that I can test you on in one, it's great. And this tells me whether you know inelastic collisions, conservation of momentum, kinetic energy, energy in general. You can do a little trig because you have to do a little trig to find that angle. All sorts of fun things. There's an example in our book, but like I said, there's a million examples of the ballistic pendulum online. People love to explain it because it covers a whole bunch of bases. So make sure you know how to do it. All the collisions that we did in 1 dimension. They can happen in 2. So you could have, a mass traveling this way and a mass traveling this way, and they hit and stick together and end up heading off at some angle there. If it's an inelastic collision, then you know M1V1 plus M2V2 is equal to M1 plus M2V final in the X and in the Y. And so in the X, right, V final in the X, would be m1 v1 initial in the x plus m2 v2 initial in the x over m1 plus m2. This guy, let's call that guy 1, and this m2 has no, so that would be your v final in the x, and similarly in the y, these would just have y's on them, and this one would be here, and this one would be 0. That would give you a v final in the x and the y, and your magnitude of v would be v final x squared plus v final y squared, and your angle would be arctan of v final y over v final x, assuming that we were measuring it from the x-axis, right? So collisions in 2 dimensions aren't much different than 1 dimension. You just have to do each dimension separately, and then if you're asked for the total magnitude and angle, find it from what we've been doing from day 1 since the math review. Okay. My final topic for the night. And one of my favorite topics that I get to do. I get to teach you how to be rocket scientists. And I'm not being facetious. And I get to talk a little bit about history, which always makes me happy. This topic, the rocket equation, is not covered very well in your book at all. There's a couple times that your book just gives you an equation and doesn't challenge you to learn where it came from. And to me, that's really, really a shame, because the rocket equation is amazing and it teaches you a lot of amazing things. And it has a long history behind it, and it actually works. You could actually use it to figure out how much fuel SpaceX needs to get off the surface of the Earth. I mean, you need some more math, but it will give you the rocket equation. The reason why it's called a rocket equation is a rocket in space is the best example. But what it really is something called a variable mass equation. So if we go all the way back to the very beginning, right? We put this in, but that mass being in there, we said, oh, well, that mass is constant. Well, what if V was constant, but the mass was changing? And I asked you last lecture to imagine things where the mass changes. Well, how about a bucket full of water that's rolling down a hill, right? Like a keg full of water, and it's leaking. So as it rolls, it's losing water. The whole system is losing mass as it rolls. The other kind of big example is what's called a coal car, and that would be a railroad car full of coal that the rocks can, the coal can fall out as it travels, and it gets faster and faster. Okay. But the rocket equation is what happens when we have variable mass. A little history on rockets. Now, there's a guy named Goddard, and Goddard had this theory before World War I that you could launch a rocket into space and fly around in space with it. And when he put forward his theory of rockets, you know, keep in mind, planes had only been around for 20 years or something. And we had steam, we had hydrogen, like the Hindenburg. I don't even know if the Hindenburg was built before he came up with rockets, but this was before World War I, or before World War II. He had come up with this idea that a rocket would work in space. And a bunch of people, you know, really smart people, are often stupendously wrong at things. A lot of people said his rocket will never work because there's nothing to push on in space. So if you were in space and you lit a rocket, it wouldn't go anywhere because the rocket has to push against the Earth to shoot into the sky. And the reason they were wrong is a rocket doesn't use a push. What a rocket uses is it uses conservation of momentum. A rocket in vacuum uses conservation of momentum to go forward. Because the fuel in the rocket and the rocket itself have zero momentum. You light the rocket and the fuel is thrown off behind you at a rapid rate. The momentum it carries behind you, you have to move forward with in order for momentum to be conserved. And because you're a closed system, momentum is conserved. There's no forces acting on you. In space, you're in a vacuum, there's no forces acting on you. If the mass shoots out backwards, you have to shoot forward with the same momentum the fuel is leaving with in order for momentum to be conserved. And we're going to look at that. So yeah, they worked. Unfortunately, the German government, the Nazis, somehow got a hold of some of Goddard's stuff. I think part of it was that the US military didn't completely believe in Goddard, but essentially the Germans made V2 rockets from his ideas. They're complicated, they're engineering. I mean, I make it sound as simple as like lighting a candle. And it is, in one sense. If you've ever done the Mentos in a 2-liter bottle, if you haven't, go get a bottle of Diet Coke and some Mentos and try it for yourself. Just be careful that you don't hurt yourself. Don't do it if you're going to hurt yourself. I didn't tell you to do it if you hurt yourself. I'm just kidding. But yeah, if you've never done the Mentos thing, look at it up on a video. It's amazing. So what's happening there is conservation of momentum. It's the momentum's leaving the bottle, so the bottle has to maintain momentum. It's pretty amazing. There's a lot of other things happening too. There's a lot of fluid dynamics happening at the nozzle and weird things like that. But for us, for now, we're just going to consider conservation of momentum and see if we can't develop the rocket equation. And then when we do fluids in a couple weeks, we're going to look at the rocket equation again using fluids, which is pretty amazing. Okay, so let's get started on this. I gotta warn you, this is a pretty high up level derivation, kind of, for some of you. Some of you might not follow this completely. All of you may not follow it completely, but I'm going to do it for you. The derivation starts that the initial momentum and the final momentum of the rocket and fuel have to be the same. So you have some rocket, and it's got exhaust, and the rocket has a mass, initial, I'm just going to call that, and the rocket is traveling at some initial speed, okay? So I'm going to call that B naught, and I'm just going to call that M. After a short time that we're going to call dt later, that just means an infinitesimal time later, the fuel that shot out of our rocket, right? Our rocket is now, and I'll explain this in a minute, moving with V naught plus dV, okay? This dm here, you might go, well, it lost that because this is actually my dm, and this is my m. But dm is negative. And we have to consider it negative because there's a weird sign issue that pops up in this. Just for now, know that dm is in itself. Think of this like a -2 or something, right? It's a negative quantity in and of itself, although in the equation it appears as a positive. And I know that doesn't make any sense. It will later. Just know that this is, dm in itself is inherently negative for way later. So we put a negative sign there, so it's positive, and this becomes positive because it would actually be negative dm. And then we say that this is V of the rocket minus V of the exhaust. And we're going to assume that the exhaust, the fuel leaving, is a constant, okay? So we're going to assume that this stuff leaves with a constant velocity. Why is this the velocity of it? Because the rocket is heading that way. So relative to the rocket, well, relative to space or something, this stuff is still traveling at the speed the rocket was going. This is like the sandbag problem in the balloon that we did for free fall, that part of our homework. As this stuff leaves, it's still traveling with the same speed as the rocket, minus the speed that it's being ejected at, right? So if VEX was less than the rocket, you would actually see it, trailing with the rocket. It would appear to be going left to right, even though it was leaving the rocket. So just know that that's true. Now, these two things are equal, but we need to figure out what this is. So we get mv naught is our final momentum. We have to do minus dm times v naught, minus a minus is plus dm times vex. And then we have to do this quadratic here, which is m times v naught plus m times dv plus dm v naught plus dm dv. So before I move this to the next page, I can cancel a couple things that you can see straight away cancel. There's an mv naught on both sides. Minus dm v naught, minus dm v naught. And so what I get here is I get 0 is dm vex plus m dv plus dm dv. So let's move this to the next page, and I'm going to move this one over. So I'm going to write m dv is equal to minus vex dm minus, if I move both of those over, minus dm dv. But I need to talk about this term right here. If I have something that's like 0.000005 times 0.000001, two very small terms are super, super small. So this term, I'm going to ignore. I'm going to throw that term away. I'm going to assume it's so small that it doesn't matter. And now I've reached my final form of the rocket equation. Almost. Okay, so if I divide by dt, right, which I can do on both sides, this, if you look at it, is force, right? And this force is equal to this constant velocity term times dm dt, which is inherently a negative quantity. So this is really a positive quantity. This term, the changing of the mass with time, is known as the mass rate or the mass loss rate, and it's generally given as R. It has units of kilograms per second. It would be something like 40 kilograms per second. That tells you how fast it's losing fuel. So this MA is minus VEX times R. That's explained in your book. And A is VEX R over M. This M is actually the initial mass of the rocket, not the current mass, it's the initial mass. And that tells you the acceleration. One thing we could do is if I gave you the initial mass of the rocket is like 10,000 kilograms, of which 7,000 kilograms is fuel. And I want to know what the acceleration is. You would compute that here. If VEX were 2,000 meters per second, right? I could compute that because this would be 2,000 and it has a let's say R is 40,000 or R is 40 kilograms per second. Okay, I could find out what A is as minus VEX R over M naught, which is 2,000 times 40 divided by 10,000. That would be 80,000 divided by 10,000, that would be 8, right? So this is minus 8 meters per second squared, right? That's the thrust though. So because it's why we have it as an inherently negative is this is the thrust that this thing's leaving with, which means the acceleration of the rocket itself is positive. It's not a huge deal. It's just the way they historically write this equation. But we've got 8 here, right? How long would it be able to burn fuel for? Well, the time, right, is R is the mass over time, right? Mass of the fuel. So the time is the mass over R, which is 7,000 over 40. And we can compute that as 7,000 divided by 40 is 175 seconds. So we would have a time of 175 seconds worth of burn. If we burn that whole fuel starting at rest, what would our accelerator or what would our final velocity be? V final is equal to V initial plus AT. We know that we're initially at rest. This is our old constant acceleration friend. So 8 times 175 is a measly 1,400 meters per second. That's nothing, right? It's not bad, but it's not great. A real rocket is going to accelerate really fast. But it could, by burning up all its fuel, it could increase. Although that's not exactly correct. What we really need to do is do a total different way of thinking about this. And this is talked about in your book, and I wanted to talk about this as well. So if we go back and look at this equation, m dv was equal to minus vex dm, okay? What I want to do is I want to find dv is equal to minus vex dm over m. Now, if I take the integral from v initial to v final and m initial to m final, right? This is a constant, it just comes out. I get on this side v final minus v initial. I get on this side, the integral of 1 over x dx is ln of x. So I get minus vex ln m final minus ln m initial. Another way to write, though, ln of a minus ln of b is ln of a over b. But if I flip it with this sign, this becomes vex ln of the initial mass over the final mass, right? Hopefully that makes sense to you. All right, so now what we have is we have that v final is the initial speed plus vex times ln of the initial mass over the final mass, right? And so what this tells us is how fast this thing will be going once it burns off all of its fuel, okay? Therefore, what you really want, and we're going to assume this is 0, what we really want in our equation, we said, what's this? 2,000? So 2,000 is vex ln of m initial over m final. Our m initial was the weight without the fuel, so 10,000. M initial is 10,000 kilograms. Our m final is m initial minus fuel. And we said fuel was 7,000, so this is 3,000 kilograms. So we get ln of 10,000 over 3,000, or 10/3, and 2,000. So our V final is 2,000 times ln of essentially 10 over 3. So 2,000 times ln is on your calculator. It's usually one of the major buttons. I get 2,407, okay? Meters per second. Actually, I'll just round up to 8. When I did this acceleration, I thought I'd only get 1,400. This is actually the true integral of it. You actually have to do it this way in order to figure it out, because what did we not take into account doing it the other way? What we didn't take into account is that the mass is changing, right? there's a variable mass here. And this way of doing it assumes that the mass is constant the whole time, and that's what our acceleration is. So yeah, it tells us the thrust initially when we turn it on, but it doesn't tell us the true acceleration. And the acceleration is going to change based on how our mass changes. So this is really the correct way to do it. This right here is your correct way. And that's also the dangers of some of the stuff that we simplify too much. If we simplify this too much, we get a very different answer than what we get. The rocket actually goes faster because there's less mass resisting the acceleration as we go, right? And that makes the acceleration faster. Anyway, if the thrust is in general the same as it goes. Okay, so that's how you do a rocket problem. That's a little bit about natural logs and a little bit about using the momentum. Notice here, all we did for this was use the momentum. Setting this up is a bit of a pain. Like justifying this part, that's probably why your book skips it. However, this is the way that you actually do a true rocket or any type of variable mass, which means that if we wanted to know what V final was, if I gave you some mass, right? Since this, remember that, where was it? A is minus VEX R over M naught. So you could find R is A M naught over VEX with a negative sign. And, or solving this for VEX, you would get minus A M naught over R is what I mean. So if I gave you the initial acceleration, the initial mass, and the rate, you could get VEX, and then figuring out this was mass initial over mass final, if I did that correctly. So this could be anything. This could be a bottle, right, of Mentos and Dr. Pepper, right? And I tell you that VEX is 10 meters per second, and I tell you that the initial mass of the bottle is 14 kilograms, and the final mass is, mass final is 0.3 kilograms. And you can tell me what the final velocity will be from rest, because this is, if it starts from rest, right? What would that be? Well, let's look at this really fast. 10 times ln of 14 divided by 0.3. It would be 38.4 meters per second. One last thing that I want to note here. If you've ever seen the space shuttle, back when we used to fly them, if you've gone to the LA Museum Science Center where they have one of them there and saw it. The idea here is that you want ln of that term to be as big as possible. So how do you make ln big? Well, you make the final mass really small. So you want the fuel to mass ratio, to final mass or cockpit ratio or whatever, spacecraft to fuel ratio to be really huge. Well, fuel to spacecraft. The bigger it is, the better your final speed will be, right? But it's ln. And effectively, what if they were the same? What if you had no fuel? What happens? If m naught is equal to m final, what is ln of 1? Well, ln of 1 is, anybody know? It's 0, I'm being facetious. I don't think you can have a negative ratio. I don't think that makes sense. I don't think you can have a ratio less than 1. And if you had a ratio of 1, you would have no fuel. So the equation doesn't make sense anyway. But the better, you're better off the more fuel you can pack in. And that's why the old space shuttles had a huge fuel tank with booster rockets that they could get rid of. because as they burn the fuel, they could dump even the part of the spaceship that contained the fuel and get their mass down so that they could get this M final as low as possible to get them going as fast as possible by the time they got up into the upper atmosphere, which is kind of cool. Anyway, so we're wrapping up now. I know I covered a bunch of topics in chapter 9. Here's what you need to know how to do though. Remember the center of mass equation for more than one particle is x COM is mx for each one plus mx, right? 1, 1, 2, 2, etc. over m1 plus m2. Know how to do that for like a triangle and know how to do it for like a rod or a group of like 3 or 4 particles. Use impulse and change of momentum. So this was force times time is mv final minus mv initial. Know how to use that, particularly like the baseball problem where we had 2 different directions where it got hit up into the air. That's a good thing to know how to do. Understand ballistic pendulum type problems, and that's where we go from momentum to energy to solve it. In fact, I recommend you try and solve the ballistic pendulum problem on your own, if at all possible. Elastic collisions, I'm not going to put up those equations, but M2 at rest for both of these. Know how to do both of these problems with the second mass at rest. Inelastic though, MV conserved, KE conserved, MV conserved only, KE not conserved, right? And just those equations you'll be able to look up. You don't need to remember them, but know them, know how to use them, try and use them to do some collisions. And then finally, the rocket equation, just know that equation, know the 2 equations, that the thrust or force is minus VEX times R, and V final is V initial plus VEX ln mass initial over mass final. And if you know those things, if you understand those 6 things, you got chapter 9 down. You'll get some homework on it. Rocket equation probably won't be on the next exam, but it may show up on the final. I know there's a really cool problem that I like that I wrote, turning Bernoulli's equation into the rocket equation, but that's for the final. That wouldn't be on the next exam. I generally don't put the rocket exam stuff on there because it's a little confusing and it's pretty much just plugging numbers in, to be honest. But you'll probably get a problem on it for your homework. So yeah, so just make sure you know Ft is equal to change in momentum. Make sure you know how to do ballistic pendulum. Make sure you know how to do elastic and inelastic collisions. And then make sure you know how to compute the center of mass. And you're all good. Long, long lecture, I know. But anyway, talk to you guys soon.